So we're going to be talking about this idea of redshift, okay? So redshift is this notion that light or waves can be stretched or compressed, all right? So in another video, you're going to be watching a car drive past, and you're going to hear, so as it's approaching you, the pitch is high, where it's like, and then once it goes past you, you hear, so really, if you're in the car, all you'd be hearing is, right? So it's just like cruising at the same speed. But from a person standing in one spot, you hear the waves get compressed and you're, right? And then as it goes past you, you're, which is the lowering of the pitch. The same thing happens with light. Light can be stretched or compressed based on if something's moving towards you or if something's moving away from you. Towards you would be a compression of the light, which is a squeezing of the light, and away from you would be a decompression or a stretching of the light. So these are colors. It's weird to think about colors as being waves, but really they are. So light doesn't have a color. When specific wavelengths of light hit the back of your eyeball detects that wavelength and your brain makes that color. So when long wavelengths of light, of visible light, hit your eye, it looks red. When really short wavelengths of visible light hit your eye, it looks purple or even blue. And then when you get a combination of all of these different lights, it looks white. So when your eyes detect every color at one time, or really red, green, and blue or violet all at the same time, your brain tells you white, all right? So I have a little test that you can do. So take a look at this with this screen real quick. I don't know if it's gonna work for you at home, but if you look from the left to the right really quick, you might see that there is a flash of different colors. If not, then in class we'll be able to do that, okay? All right, so let's keep going. So the main point is that a stationary object that emits light or sound will have an equal distance between these different waves. But an object that's emitting light or sound and is moving, if it's moving towards the right, this object is going to be compressing its waves on this side, and this object will be stretching its waves on the other side. Now, depending on which side we're at, we might see different things. So if we go back to the colors, let's say we have something that's producing a yellow light. If it's moving away from us and that light is getting stretched out, the yellow will change to more of a red light. But if the yellow light is moving towards you, the light will become more of a blue color. And now, just to be clear, we're talking really, really fast speeds. We're not talking 20 miles per hour, 50 miles per hour. We're talking like 500,000 kilometers per hour, like insane speeds that are hard to comprehend, but they're happening in the universe. So the results of an object emitting electromagnetic energy, light, and an object emitting light moving towards the Earth will be compressed, and that object will appear blue. An object moving away from the Earth really fast will appear red. All right, so here's the idea. If a star or a galaxy is moving towards you, the light will appear blue. If an object is moving away from you, the object will appear red. What does this all have to do with the universe and the Big Bang 13.8 billion years ago? I'll tell you exactly right now. When we look out into the universe at all these different galaxies, we know that the galaxies produce mostly white light. So they should look white. All right, so we'll bring it back to this. They should look white. But almost every single galaxy that we see has a red tint to it. And the further that galaxy is from us, the more red that galaxy appears. So what does this mean? An object that we know is white looks red. There's only one answer to that, and that's the object is moving away from us. So if all galaxies are moving away from us, and then if we were looking at from their perspective, all galaxies would be moving away from them. So all galaxies are moving further away from each other every single day, right? So they're getting further and further apart from each other every single day. If we play that in reverse, and we go back to the beginning of time, all those objects are at one single spot. Main point. Because we see these red-shifted galaxies, we have proof that the universe is getting larger and larger and larger. Which is proof that if we go back in time, the universe used to be smaller and smaller and smaller and smaller and smaller. All right? And stars produce these different spectrums of light. All right? So here's our spectrum. A spectrum just means rainbow. Okay? We have red on one side, we have blue on another. If this star is producing these standard lines, we know they're producing these standard lines, but we see these standard lines being shifted towards the red, or really shifted towards the red, we would say that this object is moving away from Earth, but this object is moving away from Earth faster. Now, if an object was moving towards the Earth, and it has these standard spectral lines, but they are shifted more towards the blue, we would say they are red shifted. I'm sorry. We would say they are more blue shifted. So they were originally supposed to be around here, and they shifted towards the blue. They're not in the blue, but we still call it a red shift versus a blue shift versus a red shift. I'm sorry, I keep messing that up. Main idea. Redshift is proof that galaxies are moving further away from the Earth. They're proof of the Big Bang. They are proof that the universe is 13.8 billion years old.